Hello everyone. In our earlier video, we had a slight intuition into the trigonometric ratios. Trigonometric ratios. In this video, we are going to look at it in full detail. So consider two triangles. These two triangles are similar to one another in the sense that both of them are right angles. So one corresponding angle is equal, and we are assuming that this angle is equal to 30 degrees. So the second triangle is a scaled up version of the first one because two corresponding angles are equal. So according to the double A similarity postulate, we can conclude that these two triangles are similar to one another. When two corresponding angles are equal, it also means that the third angle is also equal. Because the sum of the angles in a triangle is 180 degrees, so the third angle has to be equal to 180 minus 90 plus 30. 180 minus the sum of these two angles. So it is going to be the same for both the triangles. So these are similar. So we know that in similar triangles, the corresponding sides also are in ratio. Now if I name this triangle as ABC and the scaled up version, the second triangle as DEF, since they are similar, we can say that let's take the height of both the triangles. This is the height, the perpendicular, isn't it? Is the height of the triangle ABC. BC is the height of triangle ABC. So BC by EF, the height of the second triangle, would be equal to the longest side. The longest side, AC by DF. The longest side of the triangle is the side opposite to the largest angle, which is 90 degree in this case, and we also call this as the hypotenuse. In the case of a right angle triangle, we call the longest side as the hypotenuse. So these two ratios are equal. The corresponding sides are in ratio for similar triangles. Now our purpose for writing this ratio is to manipulate this ratio somehow and try to represent it as a ratio of one single triangle. You will understand it better when we finish it. I am just cross multiplying. I get BC multiplied by DF will be equal to AC multiplied by EF on cross multiplication. Now rearranging a little, let's take BC and AC, the sides of the first triangle, on one side. So BC divided by AC will be equal to now the corresponding sides of the other triangle, EF by DF, right? We have taken EF divided by DF. Now these two ratios also has to be equal. Since these are equal, these ratios have to be equal. And what do these ratios stand for? They stand for the height by the hypotenuse of every triangle whose one of the angles is 30 degrees. I mean every right angle triangle when I say every triangle. For every right angle triangle, when the acute angle is 30 degrees, this ratio remains a constant. And that is why mathematicians have decided to name these ratios. Since they are constant for all these triangles, they decided to name those ratios. And in order to name the ratios, we cannot keep writing it as BC, AC, EF, DF, etc. because we are going to deal with a number of triangles. So for that matter, let us just rename or look at the sides of the right angle triangle with respect to the angle concerned, that is theta. And now I am generalizing, and we have taken it as 30 degrees. Now let's generalize it to theta. So this is right angle and this is angle theta. So as far as angle theta is concerned, this side where we consider it as height, here it is opposite. This would be taken as the opposite side because it's opposite to angle theta. And the one which is close to theta, near theta, is called the adjacent side of this right angle triangle. And we know that this is the hypotenuse, the longest side. This naming is necessary because we cannot keep writing it in alphabets anymore or height by hypotenuse. Because we are going to talk with respect to the angle here. theta. That is why we are naming it as opposite, adjacent and hypotenuse. So now it would be easy for us to arrive at trigonometric ratios keeping all this in mind. And already we saw in our earlier video that opposite by hypotenuse was termed as sine theta. But is there only one ratio? There are how many ratios can there be in a three-sided triangle? We have three sides, isn't it? We have three sides, and in every ratio two sides are involved. Two sides are involved in every ratio. So totally we would be having 6 ratios, right? And we just saw one in the last video. Now we will be seeing all of them clearly. So what would be our first ratio, or let us just write down whatever ratios possible with these three sides. Of the first one, let's see what are the ratios possible with the numerator as the opposite side. It's opposite by hypotenuse and opposite by adjacent. And what if we have adjacent in the numerator? How many ratios can we have? Adjacent by hypotenuse and adjacent by opposite, right? And what if we have hypotenuse in the numerator? We have hypotenuse by opposite and hypotenuse by adjacent. So there are 6 ratios, and that is why we have 6 trigonometric ratios also, right? Our trigonometric ratios are 6 in number. So now let's see how they were named. So let me take a fresh page and redraw the triangle which we saw just now. So this is a right angled triangle, and we had just now stated that if this is 90 degree and if we consider this as angle theta, this is the opposite side. Once again I state this is opposite with respect to this theta, because if you take this angle, which would be actually 90 minus theta, because these two would sum up to 90 degrees. So with respect to this angle where I am just placing a dot, this side would be the opposite side, isn't it? So the opposite would change with respect to the angle which we are considering. So let me just erase this now. We are not bothered about this angle, so we are bothered about just theta now. So this is the opposite side, this is the adjacent side, and the longest side, the hypotenuse. So let's look at the first ratio possible. Let's take opposite by hypotenuse, and this was termed as, or this was named as, sine of theta. Sine of theta. This theta is very important here because, as I said, this is opposite with respect to theta. But in the perspective of theta, it is the opposite side. So sine of theta, it is not sine multiplied by theta or not a product of sine and theta. It is sine which is dependent on theta. So sine of theta, or just sine theta, or the short form here which we use is sine theta. So this sine theta is equal to opposite by hypotenuse. So this is one ratio, and the next one, which was named, was cos theta or cosine theta. Cosine theta, shortly called as cos theta, is equal to the adjacent side by hypotenuse. So cos of theta is adjacent by hypotenuse, and tan theta or the tangent theta stands for, this name stands for opposite by adjacent. And if you look closely, if you divide this by this, that is, if you divide sine theta by cos theta, you get opposite by hypotenuse divided by adjacent by hypotenuse. Then we arrive at opposite by adjacent, which is tangent of theta. Tangent of theta is also called as, shortly called as, tan theta. So tan theta is nothing but sine theta by cos theta. It's opposite by adjacent. We'll just see these three ratios now in this video. the other three ratios, let us look at it in the next video. And the other three ratios are nothing but the reciprocals of these three ratios. I'll just show you how. We had listed 6 ratios. And what did we see now? We saw opposite by hypotenuse, which was sine theta, right? And we also saw adjacent by hypotenuse. Adjacent by hypotenuse, which stood for cos theta. Now just look at this ratio. Opposite by hypotenuse, hypotenuse by opposite. Just the reciprocal of sine theta. That is one ratio. And the reciprocal of adjacent by hypotenuse, this is another ratio, and these two are reciprocals of one another. This stands for tan theta, and this is the reciprocal of tan theta. So we'll just see the reciprocals of these three ratios in our next video. Till then, I hope you understood. Thank you.